We're going to start talking about bonding, and actually the next couple of days we'll deal with bonding, and I believe the type of bonding that we'll be dealing with right now is the bonds between atoms. And so let's go ahead and talk about what an actual chemical bond is. A chemical bond is an attraction between two atoms, and we'll learn about the different types of bonds that are involved here as we go through this topic here. But again, it's an attractive force where two atoms are held together. And we'll talk about the strength of these bonds as we go on. So again, a chemical bond is nothing more than a strong attractive force between atoms or ions in a compound. Factors that affect the bonding, it's electrical nature. So again, when we talk about ionic compounds, we did that before the break. So are there sharing of electrons in an ionic bond? Or yeah, in other words, a metal does what to its electrons? Gives them away, and the non-metals take them. Yeah, whatever that was. And we're going to find out that with the types of bonding that's taking place between atoms of the things that we just named, there's no donation, there's no acceptance, it's all sharing. And that's what non-metals do with other non-metals, they share. So the attraction for other atoms, and you'll find out that some atoms just simply don't like each other, so they won't even make a bond. Just like you in life, there's certain people you don't like, so you don't make friendships with them or bonds. Yeah, nothing wrong with that. That's pretty normal. Again, when we talk about the structure of these atoms or what they're trying to achieve with their electrons, they want to be isoelectronic with their nearest noble gas. Non-metals are trying to get 8 electrons in their outermost s&p orbitals, where metals are trying to have none. All right. And by doing this, they'll be isoelectronic with their nearest noble gas. And again, don't forget that that only deals with the representative elements, or those elements in the s&p orbit. Ionic bonding. We talked about a little bit about this before with the metal and the non-metal. We didn't get into the details or the specifics about what was taking place. But again, what's a cation? Remember, cats are very positive, right? So if something's positive, did it gain or lose electrons? Lost electrons. So cations are metals that have a positive charge. Anions are negatively charged. Okay, so those are the non-metals when they accept electrons. So remember, cats are positive. They're very positive creatures. Okay. An ionic bond is the electrostatic attraction between a metal ion and a non-metal ion, or the electrostatic attraction between a cation and an anion. Properties of ionic compounds: in the liquid phase, they like to conduct electricity. Okay, because we have all those electrons that are free and able to move. Crystal lattices, don't worry about that. They're three-dimensional shapes that form different patterns, and we'll talk about that much, much later on. Actually, maybe not even until we get into AP. So, skip over that. Covalent bonding, whenever you hear the word covalent, the first word that I want to pop into your head is sharing. Okay, when you hear covalent, I want you to think of sharing. So when we talk about covalent bonding, there's a sharing of electrons that's taking place. And when they're sharing electrons, that helps the other atoms or each other to get 8 electrons in their outermost s&p. So they don't have to do the ionic thing where it's like, give me your electrons. No, you can have my electrons. I don't want them type deal. But when they're sharing, that gets them closer to getting to the number that they want. Okay? And again, covalent bonding never takes place between a metal and a non-metal. It only takes place between non-metals. Okay. And here's a graphic showing how, here I have a hydrogen atom or 2 hydrogen atoms. And in hydrogen, in the first row, there's only 2 boxes because there's a 1s orbital. So that's we can only get 2 electrons in that first energy level. So if we bring 2 hydrogens over, they can share those electrons by having 2. So they work together. All right, bond energy. Bond energy is the amount of energy needed to either make or break a bond. Okay? Bond energy is the amount of energy needed to make or break a bond. So when atoms are coming together, there's a certain bond energy to make that bond, and then when you give it some more energy, you could actually break that bond. Okay? So we don't do a whole lot with bond energy in here, but in AP we do a ton with that. But just know that it's the amount of energy to either make or break a bond. Even though we're not going to do any Lewis structures today, here the circles along with covalent mean sharing. So when we draw our Lewis structures, you'll draw the number of electrons that each atom is possessing, and then who is being shared with each other. Okay, so when I look at the hydrogen, all the electrons are being shared, because again, hydrogen can only have one electron, but when it's full, it can have two. However, if you look at chlorine, because there's no p orbitals here, however, when you look at chlorine or any other element, there should be a total of 8, because you have 2 electrons in the s orbitals and 6 in the p, for a total of 8. Now, chlorine comes with 7 valence electrons, each of them. So if I have 7 here and 7 here, if they share these 2 electrons here, now everybody has 8. Okay. So when we bring them together, now everybody has 8 and they're very happy. And that's what we want. We want the elements to be happy. Unequal sharing of electrons, and you'll get, I don't know if you have this table in your notes. I don't remember if you do or not. Is there an electronegative table? No, that's not. That's a diagram. Let me see if I gave you a table. I didn't give it to you, but I'll make sure that you have it, or we talk about it a little bit later on. Unequal sharing of electrons. We're going to find out, maybe not today, but a little bit farther down the road, that the chlorine has a greater desire for hydrogen's electron than hydrogen has for chlorine's electron. And we'll talk about that evidently a little bit later on. So one way that they can share is by saying, hey, hydrogen's looking over at chlorine saying, hey, I noticed that you need one more electron, and I only need one more electron. Can we get together? Yeah, let's share. Okay. It's chemistry. Brings a tear to your eye, right? I know. All right, so again, hydrogen's not giving an electron away and being empty and then making chlorine very happy, but together they can share and have 8. However, we'll talk later on, and I'll give you some actual values. Chlorine is a little more greedy than the hydrogen when it comes to sharing. It's kind of like any good relationship. Later on, when you get married, one of you will make more money than the other, but you're still sharing. Okay. All right. It's our money, right? As long as my wife makes more, I'm happy. That's okay. She doesn't, unfortunately, but all right. Polar covalent bonds. Now, again, when you see the word covalent, what does that mean again? Sharing. Now, if you see the word polar in front of it, polar covalent means unequal sharing. Okay. So polar covalent sharing means we have unequal sharing of electrons. Dear polar. Okay, so one of those has a greater attraction for those shared electrons than the other. So when we look at this type of bond here, this is a polar covalent bond. What do you think, if this is polar covalent, what do you think these types of bonds are?
Covalent.
Non-polar covalent. Okay. So you got polar, which means unequal. Non-polar means they're equal. Because again, if you are sharing with your twin, then they should be equal.
Wait, wouldn't that just be regular covalent?
No, there's no such critter as a covalent bond. It's either polar covalent or non-polar covalent. That's all right. You're just learning. All right, so polar covalent bonding means that one of the elements has a greater attraction for that shared pair of electrons, and so that electron's a little bit closer to the one atom than the other. Okay. Luke, come here a second. Come here. You're gonna be on camera.
Oh, you're gonna
Stand right there.
Are you gonna spray him?
All right. Grab on. This is an electron up here. Grab on. Down here. Okay. We are sharing this electron. Okay. When we extend your arm. Okay. This would be equal sharing. Now, if I'm the hydrogen and Luke is the chlorine, we're still sharing, but that electron's a little bit closer to Luke than it is me. Right? What charge does an electron have? Negatively charged. Now, even though I'm still sharing it, but that electron's a little bit farther away from me, I'm not feeling the full effect of that negative charge as much as Luke is. Thank you, Luke. So by that taking place, Luke had a partial negative charge because that electron was closer to him than it was me.
Is that supposed to be an 8?
It's actually a lowercase delta. So it looks like you started to make an 8, but you stopped. Okay, so
Sideways view with the little snake on it.
I'm starting to make an 8, but I stopped before I crossed, so to speak. This is the sign for a partial negative charge. This is also the sign for a partial positive charge. So when I was extended, I'm still hanging on to that electron. Yeah, we're sharing, but we're not sharing equally. That electron's farther away from me, so I'm not feeling the full effect of that negative charge. So if I were to give that electron away, what would my charge be? Positive. It would be a full-blown positive charge. And whoever received that electron would have a full-blown negative charge. However, since we're still sharing, we can only have a partial negative or a partial positive charge. Okay? So looking back at this diagram here, I'm going to tell you that the chlorine has a higher electronegative value, or a greater affinity, or a greater attraction for that shared electron that hydrogen's bringing. So in that case, Luke would have been the chlorine and I would have been the hydrogen. Yeah, we're still sharing, except I'm not feeling the full effect of that electron's charge. So I have a partial positive charge where the chlorine has a partial negative. Okay. That is what we call a dipole moment. Some people might say that's a dipole. No dipoles here. Did you say that, Kat? And later on we're going to talk about bonds between molecules, and we have a dipole-dipole. Some people are like, yeah, those are two dipoles there. All right. When they're sharing the electrons equally, then we say, okay, that's a nonpolar covalent bond. Okay. All right, this graphic shows, and ignore the hydrogen bond because that comes a little bit later on. I love how straight that is too. That's me with paste trying to be nice and straight. Here, if I look at the bond between the oxygen and the hydrogen, are they sharing that electron equally based on that sign right there? No, they're not. Who has the greater attraction for the shared electron, the oxygen or the hydrogen? The oxygen, because it has a partial negative charge. Good. That's all I wanted.
Wait, does the D stand for dipole?
Where's a D at? There are no D's on there.
D negative. Oh,
That's still the lowercase delta. All right. So here are the types of bonds that we talked about. Here, these black dots here represent atoms, or I'm sorry, nuclei. So they're not eyeballs. So when we have a nonpolar covalent bond, there's equal sharing of the electron or electrons. If it's a polar covalent, one of the atoms has the greater attraction, but they're still sharing. That's how it's together. If it's ionic, the metal gave the electron to the non-metal. So there's no sharing. Okay? Sorry. So again, here are your three different types. Nonpolar covalent means that we have equal sharing. Polar covalent means we have unequal sharing. And then ionic means there's no sharing. It's a donation or an acceptance. All right, so electronegativity, again, is the measure of the attraction or the affinity for other atoms' electrons. Okay. I can't believe I didn't give you a... Oh, here it is. No, it isn't. Did I not give you a chart? There it is. All right. This is the table that I was talking about, and I will make sure that I give you this table. I'll go back. I just want to point this out. So here are the electronegative values. So looking at the hydrogen and the chlorine, the higher the value, the greater the attraction for the electrons. Now, one thing that I want you to notice is, who has the greatest electronegative value? Fluorine. Who has the lowest? Francium. Now, here's the trend. As we go from left to right, it increases in electronegative value, and it decreases as we go down. Why do you think it would increase as we go from left to right? Non-metals, very good. And non-metals want electrons. Where metals are saying, nope, you can have it. You're good, take it. Okay. So let's go back up. So I wanted to show you that graph. I don't know why I didn't put it closer, but so again, the electronegativity is the attraction for other atoms' electrons. And the higher that value is, the more hungry it is for other atoms' electrons. So fluorine has the highest value, francium the lowest. And you will get that table that I showed you a little bit farther down in your notes. And you just have to look at it and say, oh, well, who has the higher value? Oh, that one. So that one's going to be partial negative, if they're sharing. And again, here's that trend that the decreasing, as you go down a column, the electronegative values decrease. As you go left to right, it increases. Okay? And there again, I put francium has the lowest, fluorine has the highest. Okay? There's your table, so you have a copy. All right, predicting the types of bonds. So we talked about ionic, we talked about polar covalent, we talked about nonpolar covalent. So now you're going to have to be able to decide, if I'm looking at a molecule, which of the three am I looking at? Okay? So the way that we do that is we take the differences of these values here. Okay? If the value, generally speaking, is 1.7 or greater, we say that it's an ionic bond between the two atoms. If we say that the value or the difference in electronegativities is between 0.1 and 1.7, we generally say that's polar covalent. Now, there are some exceptions, and we'll talk about that here in a second. If the difference in electronegativities are 0, so like when we looked at chlorine earlier, I take 3.0 minus 3.0, I get 0. Then that means I'm looking at a nonpolar covalent bond. Okay? So again, these are just generalities, and we'll talk about when you can figure that out. So again, whether they're sharing, not sharing, or sharing equally. Okay? All right, so let's do some example problems. Let me turn the lights on so you can actually see these. Does everybody have the blanks up to this point here? Because I'm going to turn the lights on. We got to.
Oh no.
Oh yeah.
Wait, are we stopping after this practice problem?
That's our homework. At these three different compounds here, or I'm sorry, molecules, because they're not all compounds. And let's find out what type of bonds they have. So again, if your difference in electronegativities is 1.7 or greater, we will say that's an ionic bond between the two atoms. If it's between 0.1 to 1.7, then we say that it's a polar covalent bond. If it's 0, then it's a non-polar covalent bond. Okay? And I'm going to have you help me with the values since I don't have the chart in front of me. So looking at the first one, HBr. Okay? I know that hydrogen's 2.1. What's the electronegative value for bromine? 2.8. 2.8? Okay. Does everybody see? Should look something like this, and you will get this on the test. Okay. So the hydrogen up in the top left is 2.1. The bromine is 2.8. Now, we always want to take the absolute value of the difference. So even though you might get a negative value here, and you would if you did 2.1 minus 2.8. So that's a difference of 0.7, right?
Yeah.
So where does that fall? Polar covalent. Very good. So we can say that we have a polar covalent bond between the hydrogen and the bromine. Okay? Now, what's that? Oh, okay. So we know we have a polar covalent bond. Who has the greater attraction for the shared electrons? The hydrogen or the bromine? The bromine. The higher the number, the greater the attraction. So if I were to ask you to, hey, designate a charge on that, that would be a partial negative, that would be a partial positive. In other words, they're not giving their electrons away, so it's not a full-blown charge. They're still sharing these electrons that are between there. Okay? But that shared electron's a little closer to bromine, so bromine's experiencing that part of a negative charge. So partial negative, partial positive. Higher the value, the more negative it is. Okay? All right, let's look at NaF, sodium fluoride. Okay? What is the value for the sodium? 0.9. And fluorine, 4.0.
How do you know?
Again, your
Oh,
table.
I wasn't looking at that.
Yeah.
Okay.
So the difference between those would be 3.1. We'll take the absolute value of that. So 3.1 tells us that we are ionic. And that's good because we have a metal. Anytime you have a metal, and please listen, metals are over here again. Anytime you have a metal, no ifs, ands, or buts, it is ionic. Okay? No ifs, ands, or buts. If you have a metal in your compound, and you'll never have two metals together, but if you have a metal, it's ionic. Sometimes you might get the math to be like 1.6, 1.58, something like that. If you've got a metal in there, it's ionic. Don't even question it. Now, since this is an ionic bond, what's happening? Are they sharing electrons?
No.
No. So what is sodium doing? Giving away its electrons. So how many is it giving away?
I mean,
1, because it's in group 1A. So sodium will have a +1 charge. So if it's an ionic compound, you got to tell me how many electrons it's giving away. And fluorine's accepting how many? 1. So it'll be a negative charge. Okay? So ionic has full-blown charges, where polar covalent has partial charges. All right, looking at nitrogen. What's the value for nitrogen?
Oh, we just put in 3.
3.0. Okay. So 3.0 minus 3.0 is 0. So it's a nonpolar covalent. Which means what? Nonpolar covalent bonding has what type of bonding between? They're equal. So what type of charges do we have here?
no charge.
No charge. Because again, if they're sharing them equally, that means they're equal distance apart from each other. There's no greater attraction for the shared electrons. Here, again, the bromine has a greater attraction for those shared electrons, so those electrons are a little closer to the bromine than the hydrogen. So it experiences a partial negative charge, or part of a negative charge. Here it's full blown. The sodium said, here you go. That electron's yours. So it lost it, gained it, so full charges. No charges here. Okay? All right, let's take a look at the homework here. That's not yours? All right. Looking at the first one. Let's look at the first one, shall we?
We shall.
Unless you don't want to.
That's
Okay.
me, that's
Do not let the charge throw you off. All right, don't freak out when you see the charge, because again, what is OH negative 1? What is that? It's a polyatomic. What's the name of that polyatomic?
hydroxide.
Hydroxide. Very good. Okay.
Yeah.
Now, as a result of these two being together, it has a negative 1 charge, but it doesn't have anything to do with how they're sharing. All right. So it's not like we're showing the charge on the oxygen and we're showing the charge on the hydrogen. The reason why it has a negative 1 charge will make more sense when we do the Lewis structures, but we're not going to go there for right now. So whenever you see charges, just ignore the charge, okay, and go back to our what type of bond is in between. So looking at between the oxygen and the hydrogen, what's the value on the oxygen? Your electronegative value?
3.5.
3.5? Okay. And what is the value on hydrogen? 2.1. So the difference between those two, 1.4? So where does that fall? So since it has a value 2.1 and the oxygen is 3.5 and the difference is 1.4, what type of bonding do we have between the oxygen and the hydrogen? What type of bonding? What is it? Polar covalent? Okay. So we have polar covalent bonding. Now, since we're sharing, but we're not sharing equally, who has a greater attraction for those shared electrons? The oxygen. So the oxygen actually has a partial negative charge,
Oh, because it's bigger.
and the hydrogen has a partial positive. Very good. Okay. So again, the higher the electronegative value, the more negative that element's going to be, whether partial or full-blown negative charge.
Will we always write those half-eighths every time?
If it's polar covalent, yes. If it's an ionic, you're going to tell me what that charge is. If it's non-polar covalent, then there is no charge. Let me find you another one. Let's look at number 6. I hate to do all your homework for you.
I know.
Okay. Here's one. MgO. What's the value for the magnesium here? 1.2. And oxygen is, we just said 3.5. So the difference there, and again, absolute value wise, 2.3. Okay. So what type of bond is taking place between the magnesium and oxygen?
Do you subtract them backwards?
It's absolute value. So you find it and then drop the negative if we have it.
Mg is a metal. It's ionic.
Well, it's ionic because it's 2.3.
Or it's also-
And because magnesium's in there. Very good. So we know it's ionic. Before we even did the did the problem, the math, sorry, we knew that it was going to be ionic. Okay. So in AP chemistry, when you do this, you're going to look in, you won't have these values, but that's okay. Because if it's a nonmetal with a nonmetal, it's some type of covalent. If you have a metal with a nonmetal, then some type of ionic. All right, so what would the charge, or how many electrons is magnesium going to give to oxygen? 2. Very good, Lee. So we don't just put a plus charge, we actually put how many it's going to give away. So actually, magnesium would be a +2, oxygen would be a -2 charge. Yeah. Yeah, show the charges.
That's only for ionic.
For ionic, full-blown charges. For polar covalent, partial charges. Now, we don't have to worry about saying, that's got 2 partial charges, and that's got 1 part. Don't worry about that. Just on the ionics. Okay?
What about the
On the nonpolar covalent? The nonpolar covalent, and I don't know if I have any more on there.
There's
But,
number 2.
yeah, let's not do that one here. Let's do something like bromine. Okay? So, looking at this, and this is not on your homework, but if you want to put it on the bottom or the back, that's fine. So you have Br and Br, and the value for bromine is 2.8. So what type of bonding do you have, or I'm sorry, what's the difference in the electronegativities? 0. So what type of bonds do you have?
Non-polar covalent.
Nonpolar covalent. So who has the greater attraction for these shared electrons, bromine or bromine? They're the same. So there's no partial charges, there's no charges. So that's it. Okay? So what I want you to do on the homework is I want you to show the difference in electronegativities, give me a value, tell me if it's polar covalent, non-polar covalent, or ionic. If it's polar covalent, make sure you show me the partial charges. If it's ionic, show me the full-blown charges. This might take you 10 minutes. Yeah.
For the polar covalent, and then how do you figure out which one's the negative?
The greater the value, the more negative it'll be. So if you look at the oxygen, even in the ionic, it has a higher value than the magnesium. This has a higher value than the hydrogen. And notice they're both negative. Isn't that cool? What is it?
Like on number 7, it has like a chart of the oxygen and the voltage 4.
Oh, okay. Yeah, let's do that. Good question. So that's one of our, that's a polyatomic that's not one of ours. It's arsenate. So ASO4 -2, is that right?
-3.
-3. Okay. So here, and we haven't drawn these things out yet, but really what it looks like is this. We'll have an oxygen, and an oxygen around, okay? So what I want you to do is find out what type of bond we have between each arsenic and each oxygen, okay? So what's the value for the arsenic? 2.0. So let me do this. So off on the side here, AS and O. What was it, 2.0?
2.0.
And the oxygen's 3.5. So what's that difference there?
1.5.
1.5. So what type of bond do we have?
Polar
Polar covalent, very good. And who, or do we have a charge on each of these?
Yeah.
Who is more negative?
The
Oxygen. Is it a full-blown charge or a partial charge? Partial. So we'll say that that's partial negative, that's partial positive. Again, whichever one has the higher electronegative value, because the one that has the higher electronegative value has the greater attraction or affinity for those shared electrons. Okay. Some just want it more than others. Metals could care less. But if you have two nonmetals together, then we got to show that. Okay. Any other questions on there? So the same thing with any of the others, like number 8, where you have the carbons and the hydrogens, and yeah, we'll do the same thing as this. Everybody good? All right, you should be done before you leave today.